And now we're going to cover chapter 34, which deals with solubility. Many natural processes depend on the precipitation, that is, the forming of a solid, or dissolving of a slightly soluble salt. Insoluble does not mean 100% insoluble. By definition, when something is classified as an insoluble salt, that means that less than 1.01 molarity of it goes into solution. So that means that some of it still is dissolved in solution, some small amount, 10 to the minus third, 10 to the minus seventh, some small amount. In the next section, we'll look at equilibrium of slightly soluble or nearly insoluble ionic compounds. The equilibrium constants can be used to answer questions regarding solubility and precipitation. How much do we expect to dissolve? Or how much do we expect to dissolve before precipitation occurs? In other words, how much dissolves before we reach something called the saturation point? That's the point where we have that solid starting to precipitate out of that solution. When an excess of a slightly soluble ionic compound is mixed with water, an equilibrium is established between the solid and the ions in the saturated solution. So basically, if you have a container and you're adding a substance to it, it's going to dissolve and it's going to form ions, okay, dissolve into that solution. When it reaches something called the saturation point, that's the point where that solution cannot contain any more ions than it already has. Then what you're going to do is form solid at the bottom, or precipitates. Okay, it could be floating around within the solution itself, doesn't have to be at the bottom, but solid and precipitates will be forming. Now, when we reach that saturation point, what happens is we form an equilibrium, okay, between the ions and solids. Basically, as ions are colliding, they will form solids. At the same time, though, solids will break up and form ions, and what we get is the dynamic equilibrium between the ions and solids. The concentration of those ions will remain some constant value. Okay, and that concentration of the ions will remain some constant value. So basically you have an exchange going on. As fast as ions are colliding to form solids, you have solids breaking up to form ions, and we get this dynamic equilibrium. Similar to what we talked about back when we talked about acid base and Kc and Kp stuff. Okay, when we're talking about equilibrium. Insoluble salts will have extremely small quantities of salt dissolved in water. Okay, and an equilibrium will be established when the salt reaches its saturation point. Basically that point where they exchange from solids forming ions and ions forming solids, okay, in solution. Let's look at an example of calcium oxalate. This is a soluble salt. We write insoluble salt. We write this the same way that we write a soluble salt. You take a soluble salt, you break it on an ionic bond and form its ions. Okay, so we do the same thing here. You got calcium oxalate, which is an insoluble salt. We break that ionic bond and we form calcium ions and oxalate ions. Same way we have written the soluble salts. Major difference though is instead of a single arrow, meaning 100%, we write a double arrow. Same scenario we did with a strong acid and a weak acid. Strong acid, we wrote it the same way as we did a weak one, except we had a single arrow versus a double arrow. Same thing with the salts. Write them the same way, except we have a single arrow versus a double arrow. So what this is telling me in this equilibrium that I have calcium ions. I also have oxalate ions floating around in the solution. Now, if I'm at the saturation point, then we're going to form calcium oxalate solid. Okay, we'll precipitate out calcium oxalate. And what's happening here is we've got an equilibrium going on where I have calcium and oxalate combining to form calcium oxalate, as well as calcium oxalate breaking up to form ions. And in essence, the concentration of those ions remains concentration of the ions remains a constant. At the saturation point. Now, that concentration of the calcium and oxalate is going to be a very small amount, a very little amount that forms ions. It doesn't take much for this to reach that saturation point. When an excess of a slightly soluble ionic compound is mixed with water, an equilibrium is established between that solid and the ions in the saturated solution and is represented by a constant that is temperature dependent. Okay? The equilibrium constant for this process is referred to as the solubility product constant, or KSP. So how do we set up that equilibrium? Well, the same thing we did in the past. You got to write your reaction, and then we take products raised to their coefficients, divided by the reactants raised to their coefficients, realizing that liquids and solids are not part of the equilibrium. So in this particular case, if I was going to set up my K expression, I would be my concentration of my calcium times the concentration of my oxalate ion, both of those raised to the first power because they have coefficients of 1 and then equal to K. And since we're talking about the solubility product here, we refer to it as KSP. We get a subscript of SP, meaning the solubility product constant. Now, you must realize that when we did the KC, KP stuff, we had coefficients to deal with, and then we got into the acid-base stuff where everything was 1-to-1, so we didn't have coefficients to worry about. But once again, in these salts, we're going to have to deal with coefficients again. You're going to have things with coefficients in front that you're going to have to raise it to powers of 2, 3, etc. Now, this solubility product constant is the relationship of the amount of ions in solution. Okay, how much is ions in solution? So it's related to the amount of ions in solution. If I have a saturated solution and I know the concentration of calcium and I know the concentration of oxalate and I multiply the two, it's going to give me this KSP value. However, if I'm not at a saturated solution and I take the concentration of my calcium, my concentration of my oxalate, and multiply them, I will not equal to KSP. Remember, it has to be your saturated, got to be at the saturation point for the concentration of these species. Okay, got to be at the saturation point. If I am and I multiply it, I will be equal to that KSP. Other thing to realize is that K is unitless and also temperature dependent. Okay, unitless and temperature dependent, same thing we did when we talked about the other K's in the previous chapters. KSP basically is a relationship of the amount of ions in solution at the saturation point. Once a product of concentrations of ions equals KSP, then we have precipitation occurs. If we before that point, the product of the concentration of ions does not equal KSP, then we will not have precipitation. This KSP is a measure of how much of the species is in the solution in ions, okay, at the saturation point. In general, the solubility product constant KSP is an equilibrium constant for the solubility equilibrium of a slightly soluble or nearly insoluble ionic compound. It is a constant that relates to the amount of substance that is dissolved in solution, so it's related on the amount dissolved in solution at the saturation point and not the amount in the flask. Only the amount dissolved. You can care less how much solid's in there as long as you pass the saturation point. It could have 1 gram, 100 grams, doesn't matter how many grams of solids there. What we're doing is measuring the amount of ions, and we have to be past that saturation point to be measuring that amount of ions in solution. Okay, that KSP is a relationship with the amount of ions in solution in a saturated solution. It equals the product of the equilibrium concentrations of the ions in the compound. Okay, accounting for solids have an activity of 1. Each concentration is raised to the power equal to the number of such ions in the formula compound. So once again, we've got to account for those coefficients, which we didn't have to do when we were talking about acids and base stuff because everything was 1-to-1. For example, let's look at lead iodide, lead 2 iodide. It's an insoluble salt, so it's going to break up on that ionic bond and form lead 2 ions and iodide ions. But since there's 2 iodines part of that formula of lead-2 iodine, I have to have 2 iodines in my formula. If I want to write the KSP for this equation, in this case it'd be my products, which are going to be concentration of my lead-2 to the first power, time the concentration of my I minus to the second power. So the KSP looks like this: concentration of lead-2 ions time the concentration of my I minus to the second power. Notice that I had to account for that 2 coming from that coefficient on my balance equation. This is the product of my ions at saturation. So if I'm at a saturation point and I know the concentration of my lead, concentration of my iodide, and I square that value, I'll be equal to that KSP of that lead-2 iodide. Now, if I'm before the saturation point, this equation will not hold true. This equation holds true only for I'm at the saturation point or beyond. Let's look at an example calculating the KSP. We did this previously in the other chapters. We calculated Ka, Kb, Kc, Kp, etc. Okay, before we actually use those values to do calculations. So we're going to do the same thing here. We want to take a scenario and calculate the KSP. I have a 1 liter sample of a saturated calcium oxalate solution. Contains 0.0061 grams of a salt at 25 degrees C. Calculate the KSP for this salt. Okay, an important word in this whole word problem is saturated. It is a saturated solution, which is telling me I have 0.0061 grams of the salt per liter, okay, at the saturation point. That's telling me my solubility of this compound. If I wasn't at the saturation point, I couldn't calculate the KSP. I have to be at the saturation point. Now with the KSP, everything is concentration based, so one of the first things we're going to have to do is change that from grams per liter to moles per liter. Okay. The solubility of your calcium oxalate was given to us as 0.0061 grams per liter. I need to convert that to moles per liter. Okay. If we talk about grams per liter, that is a term that we use as solubility of the substance. While if I use moles per liter, that's something we call the molar solubility of a substance. So to calculate that, I'll take my 0.0061 grams of calcium oxalate per liter, divide that by its molar mass, which is 1 mole of calcium oxalate divided by 128 grams of calcium oxalate. My grams cancel, which leaves me in moles per liter. So I got 4.8 times 10 to the negative 5th moles per liter of calcium oxalate. Now this is telling us what we refer to as a molar solubility. That's how many moles I can have in solution of the maximum amount. This is the maximum amount of calcium oxalate that can go in solution. If I go beyond this amount, that's when I start forming solid. Okay, so say for argument's sake, if I had 5 times 10 to the negative 5th molarity of calcium oxalate that I was going to put in solution, 4.8 times 10 to the negative 5th will be dissolved as ions. The rest of it, the other 0.2 times 10 to the negative 5th, will be as a solid. It will precipitate out. Okay, so the other 0.2 times 10 to the negative 5th will be in excess, and that will be as a solid. Okay, the maximum amount that can be in solution is 4.8 times 10 to the negative 5th. Anything in excess, that's going to end up being as forming that solid in that dynamic equilibrium, that saturated solution. So when 4.8 times 10 to the negative 5th moles of the solid dissolves, it forms 4.8 times 10 to the negative 5th moles of each ion. So in essence, that's telling me I have my equilibrium, my calcium oxalate. Usually we take that salt and we break it up. So I got calcium oxalate. We know that I have 4.8 times 10 to the negative 5th molarity. Okay, that's the maximum that we said that can be in that solution. Okay. That's the maximum being in solution, okay? So we can figure out how much calcium there and how much oxalate for my mole-to-mole ratio. Since I have 4.8 times 10 to the negative 5th molarity of calcium oxalate, for every 1 calcium oxalate, I got 1 calcium, so I get the same concentration of calcium. Same thing holds true for the oxalate because that's also a 1-to-1 mole ratio. So that tells me at equilibrium I have 4.8 times 10 to the negative 5th calcium, 4.8 times 10 to the negative 5th oxalate. Same thing we did with the soluble salts. Except the soluble salts has a larger threshold of how much can be in solution. For the insoluble salts, there's only a small amount that can be, in this case, the maximum 4.8 times 10 to the negative 5th molarity. Okay, so they have smaller numbers, but we break it up the same way, and it also tells us the amount of ions in solution for our two species of cations and anions. Well, I know that the amount of ions in each one. All I got to do now is set up the relationship between calcium and oxalate to that KSP expression, which means I have KSP is equal to the concentration of calcium to the first times the concentration of the oxalate to the first. Okay. Plug in my values, 4.8 times 10 to the negative 5th for calcium, 4.8 times 10 to the negative 5th for oxalate, which gets me KSP is equal to 2.3 times 10 to the negative 9. So this is the KSP for calcium oxalate, so I can use that number if I wanted to figure out how much calcium or oxalate I needed for precipitation to occur, which we talk about that later with problems. I can then go on and do those type of calculations. Okay, but right now we're just calculating KSP from a saturated solution. Notice that the value of KSP is a very small number, which means it doesn't take a lot of it before it reaches that point of saturation, so the concentration of the ions is very small. Let's look at this one. My experiment has found that 1.2 times 10 to the negative 3rd moles of lead-2 iodide dissolves in 1 liter of water at 25 degrees C to reach the saturation point. What is the KSP? So once again, I'm trying to calculate the KSP. Once again, we're at the saturation point, so it's telling me my molar solubility. In this case, since it was so many moles per 1 liter, it tells me my molar solubility. So I know I have 1.2 times 10 to the negative 3rd molarity of lead-2 iodide. Okay, molarity of lead-2 iodide. That is the molar solubility. That is the maximum amount that could be in solution. So if I have that amount lead-2 iodide, then how much lead do I have? Well, there's a 1-to-1 ratio, right? So it's the same amount, 1.2 times 10 to the negative 3rd. Well, how much iodide do I have? Well, in this case, there's a 1-to-2 mole ratio. So therefore, I have twice that amount. So I got 1.2 times 10 to the negative 3rd molarity of lead iodine, lead-2 ions, and I have 2 times 1.2 times 10 to the negative 3rd in iodine. Now, one thing to keep in mind here is, in this particular problem, I'm coming from molar solubility, okay, molar solubility to the amount of lead and to the amount of iodine. That's why I got to double that iodine here because of that mole-to-mole ratio. That's not going to happen every time. You're going to have to look at the data given to you. Okay? Sometimes you will double it and sometimes you won't. Depends on the information given to it. In this particular case, we're given molar solubility, and I was trying to go into the ion concentrations. I needed to do that relationship. If as a case I'm given the amount of ions, I'm not going to account for that too. Okay? Which I'm going to show you in another example later on in this chapter. So, we now write out KSP, which is your lead-2 ion concentration to the first power, time the concentration of your iodide, okay, squared, which is 1.2 times 10 to the negative 3rd for the concentration of lead, 2 times 1.2 times 10 to the negative 3rd, that whole thing squared, because that represents the total concentration of I minus, which in other words is 1.2 times 10 to the negative 3rd times 2.4 times 10 to the negative 3rd squared. Okay. Continuing on, KSP is 6.9 times 10 to the negative 9th. Important things to realize here, okay, is that I had to double the concentration of that iodine because it's coming from that molar solubility. Okay, it came from that molar solubility. I was trying to figure out how much I minus was there. There was a 1-to-2 ratio, so I had to account for that. And the other thing you got to account for is that square, on that iodide. That's coming from that balance equation, okay, due to the order of that elementary reaction, okay. Those are important things you got to realize, okay. The power is going to happen every time, goes by the coefficients. The doubling, though, this part's going to depend on how the question's worded. As I said in the next example, we'll show you what I'm talking about in that. Homework 40, okay, has questions talking about the KSP and calculating the KSP.